Share screen. Fuck. Alright, so for now, we're just gonna go over the syllabus real quick, just do a quick look-sees. So, skip all this stuff. Skip all the legal stuff. Alright, so there's a bunch of stuff at the beginning of the semester. We're gonna cover a majority of the structural stuff near the beginning of the semester, just as a review, and we're gonna cover like a little bit of the second part of the semester. Because like the rest of the stuff is like just notes that you should have gotten from the lectures. It's not really anything conceptual, so. And I also don't know how to like go over it, and so like same thing with environmental. There's not really there's like conceptual stuff, but it's honestly just note taking and paying attention in class for environmental stuff. So we're going to be going over quite a bit of structural stuff today compared to environmentals. So I think we're just going to start with environmental for now. I mean structural. Right. So at the beginning of the semester, what did we first talk about? We first talked about vectors. Yeah, vectors. Fun. All right. So now vectors, they are. I should open up my notes. All right. So vectors, they have a magnitude and a direction. So however, how strong this is, let's just say this has a magnitude of 5, right? And has like a direction of 30 degrees. You know, just like two variables for a vector, right? And then you can divide this vector. You can separate this vector into its component parts. Can separate it into separate it into the x and a y vector, right? So you have the x vector right here. I'm just going to do this in here. So you have the x vector right here. See how it spans the entire length in the x direction? Right there. And then you have a y vector right here. See how it spans the entire length vertically. So why is this important? Well, that's how you that's how you simplify vectors in order to add them, because you can't really add two vectors if they're going at different angles. Like it's not intuitive, and there's no really straight answer to like add the vectors unless you just like get out your ruler and measure them, you know? So you can't really measure them accurately if you just have these two variables, you know, a direction and a magnitude, direction and a magnitude. You can't really add them with just those two numbers alone, so you have to split them up. So how do we do that? Well, you all remember trigonometry? So, TOA, right? So for sine of theta of a given angle is equal to the ratio between the opposite side over the hypotenuse. I'm just going to draw a triangle real quick. So you have the right triangle, right? Right angle. And then you just pick one of the two remaining corners that will be your theta that you'll be using. So the side directly opposite to you is opposite, of course. The hypotenuse is the longest side. So that would be opposite from the right angle hypotenuse. And the remaining one, which is adjacent to the to theta and not the hypotenuse, is adjacent, right? Sine of theta equals opposite over hypotenuse. The cosine of theta would be equal to ratio between adjacent over hypotenuse and tangent. Same thing, except it's the opposite over adjacent, right? All right, so let's just, oh, well, you know what? We can just use that. Right, so how do we go about doing this, right? So we're trying to take this vector and then break it into its component parts, right? So you need the x and the y. Now, the x and the y would line up with what the adjacent side is and the opposite side is, right? So adjacent, and we know the hypotenuse is equal to 5, so we would just use two equations that both have hypotenuse, which is a known factor, and either opposite or adjacent. So we'd be using sine and cosine. Right, so how does this work? So let's just do sine theta first. Sine of theta equal to opposite over adjacent, right? So we know theta is 30 degrees in this example. We don't know opposite, so that would be what we were looking for. And hypotenuse is our 5. So just move 5 to the other side. 5 sine of 30 degrees is equal to opposite, so opposite would equal, I think, 2.5, right? Yeah, it's been a while since I've been in trigonometry. Sine of 30. Yeah, 2.5. Right, so let's do the other one, cosine. See, that also has a hypotenuse. Cosine of theta is equal to adjacent over hypotenuse. So now we have to look for a. So cosine of theta equals cosine of 30 degrees is equal to a adjacent. We don't know that. H is 5. Move 5 to the other side. 5 cosine of 30 degrees equal to adjacent. So that would be 5 cosine of 30. Wablamio. A is equal to 4.33. Yeah, it's just 4.33. Right? So what can we do with this information? Well, so this is equal to 5. This is equal to 4.33. This is equal to 2.5. And this is equal to 30 degrees. Now, y'all remember Pythagorean theorem? You can take the square root of the sum of the squares of these two, right? Hypotenuse squared equals opposite squared plus adjacent squared. You could also, a lot of you have learned it as c squared equals a squared plus b squared. But with our trigonometry triangle, we have our h squared, o squared, and a squared. So you can just figure it out. You can just solve it real quick just to see that it matches. So square root, you know what, I'm just gonna bring this up. You can see, where's the square root button? Square root of 4.33 squared plus 2.5 squared is equal to, that's fairly close to 5, right? So see, math works. All right, moving on. So what can you do with these? Well, remember how I said you had to add them together, right? So file. Resize 50%. All right. So, right. You can add it to another vector, right? So let's say you have a vector right here and a vector right here. Well, a vector, you want to add it to this vector, right? So you say this degree is 60 degrees, and it's a magnitude of 3, right? Yeah. Let's do that real quick so you can explode this into its component parts. You have the x and the y right here. So cosine of 60 degrees is equal to Adjacent over hypotenuse, so it'd be, oh gosh, it'd be A over 3. So cosine of 60, that'd be A equals 1.5 sine of 60 degrees is equal to opposite over 3. 3 sine of 60 degrees is equal to O. O is equal to oh geez, 3 sine. That seems about right. 2.59. Right. So you have these two vectors. You have this vector where it's 5 to 5 in this direction, and then you have this vector which is 3 in this direction. So you see how it's shorter, and then we just add the two together. Just gonna take this, and oh gosh, I'm gonna plop it on the end of this one right here, this vector right here, to get a new vector. See that? Bam. That's our resultant vector. How do we do that? Well, you can first off by adding all the component vectors. So so you add opposite for this one was 2.5. So we're just gonna do the y first. Actually, let's do the x first. So x would equal both of the adjacents, surprisingly. So adjacent for this one, that would be 4.33, 4.33, and then adjacent for this one would be 1.5. But you see how this is going in the negative direction, it's going left, so you have to subtract it. See, if you would add 4.33 and 1.5, your vector would be somewhere over here. But no, it's going the other direction, so you would subtract. X would equal 4.33, 2.83. Fun stuff. Now let's do y. So y would equal, where is it? 2.5. O for this one is 2.5, and the opposite for this one would be 2.59. So y would equal, that would just be 5.09. Right, fun stuff. And that seems about right, you know? That's about 3, that's about 5, and looks pretty fun, right? So you have this new vector. So you have this new vector. This one, I just redrew it over here. You have this new vector, which is 2.83 and 5.09, the x and the y. So how do we make use of it? Well, we can use Pythagorean's theorem. Square root of 2.03, oh gosh, 3 squared plus 5.09 squared, that'd be 5.47. Oh gosh, hello. Thank you, Windows. Got, so your resultant vector, let's just do v. Resultant is equal to 5.48. Cool, are we done? No, we are not. So we have to find this angle. How do we find that angle? Well, back to trigonometry, you would use tangent because it has O and A. So now you sort of like do the same thing that we did to find the component vectors, but now you sort of use it in another way, right? So you have so you have this, geez, what am I going to say? So you have this formula, tangent of theta is equal to O over A, Right, so you already have O and A, right? You have opposite. So this is your theta right here. You have your opposite side, which is 5.09. Your opposite side, which is 5.09. And then your adjacent side, which is 2.03. I'm going to use the same colors. Just cover this in green. Actually, I'm just going to make that green. All right. So you have your y right here, which is 5.09. So that's going to be your opposite, right? Opposite. And then you have your x, which is 2.83. Right? Yeah, 2.83. So that would be your adjacent. But what the frick is your theta, right? Right. So fun stuff, you just plug all this in. Tan of theta is equal to opposite 5.09 over adjacent 2.83. Oh gosh, how do we find this now? Well, you just take the inverse tangent. So tangent equals inverse, or theta equals the inverse tangent of 5.09 over 2.83. So tangent would equal, let me just check my mode, yeah. Second tangent, so you get your inverse tangent, 5.09 divided by 2.83, right? That's not right, oh gosh.
Wait. And the previous one, you did 2.03. Isn't it 2.83 or?
Did I not put 2.83?
Wait, on the calculator, right? Above?
Yeah, oh gosh.
In the square root. Is that supposed to be 2.83, right?
That should be 2.83.
Okay, cool. I just want to make sure. My bad. I just want to make sure.
Oh, that's my bad. Jesus. All right. So we'll just redo that one. 2.83, so 5.82. So that was all right.
So that's the hypotenuse value, right? 5.82.
5.82. Jeez. Right. So we do inverse tangent 5.09 divided by 2.3, and that would be 60.9 3, right? Degrees. So you have your two components that you need, and you see, yeah, that is approximately 60 degrees. Any questions? Cool. Let's move on to equilibrium. Right. So vectors, like very basic mathy stuff. But now we will be talking about what are they called? Beams. Right. You have a beam right here. Well, let's first go over the difference between all the connections, right? So this sort of connector, it's a roller. There's only a reaction. There's only one reaction in the y direction. You have a pin. There's two reactions in the y and the x. And then you have, I forget what these are called. Cantilever. Hold up. Frig. What are these called? They're called fixed. Okay, fixed points. So they have a reaction in the x, in the y, and a moment reaction. We'll get to moment in a bit, because that is very important. Right, so let's say we have a beam, right? Bam, bam, bam. Right, so you have a pin and a roller. And you're gonna have 2 reactions. I'm gonna make this slightly bigger. Right, so you have your pin. That's not what I wanted. And you have a roller. Right, so fun stuff. What do we do with this? Right, so we know there's a reaction in the x direction. I'm gonna call this point A and point B. Reaction in the y direction and a reaction in the x direction. And then we have one reaction over here because it's a roller. Only one reaction. RY B. Fun stuff. Now, let's put a load on it. Right? Put 2 loads. Right here. That's gonna be 50 kips. And let's put another one right over here. That's gonna be like 20 kips, right? And we're just gonna define some distances, some points. So this is gonna be point C, and this is gonna be point D. This distance is gonna be 5 feet. This distance is gonna be 10 feet, and this distance is gonna be 15 feet. Right? What do we do with this? So we gotta find the reactions, right? Let's do reaction at x. Let's take summation of reactions. So there are 3 different types. Reactions in the x direction, reactions in the y directions, and moment reactions, summations of moments. Frick. Yeah, so take the summation of forces in the x direction. My bad. Summation of forces in the x direction. There's only one. We're gonna assume right is positive. There's only one RXA. That's positive, so that's going right, so it's gonna stay positive. And as we all know, summation of forces has to be equal to 0, so 0 is equal to RXA. RXA is equal to 0. Very simple stuff right there. All right, so now let's take summation of forces in the y direction. Let's go assume up is positive, summation of forces in the y direction, right? So we have RYA, that's going up, so it's positive. We have this 50 kips, it's going down, so it's negative, minus 50 kips. Another 20 kips going down, so that's going to be negative 20 kips, RYB plus RYB. It's going up, so it's going to be positive. Summation of forces have to be equal to 0, so 0 is equal to RYA plus RYB minus 70. Yeah, 70 kips, right? So RYA plus RYB is equal to 70 kips. Fun stuff. We can't really do anything with that right now because now we're going to take summation of moments. Right? Okay. Summation of moments. Now we got summation of moments right here. Let's just take them at A. Right? Summation of moments at A. We're going to assume counterclockwise is positive. Right, so RXA, that's pointing directly at A. So it goes directly through that point, so we're not going to include it. RYA also goes directly through that point, so we're not going to include it. So summation moments at A is this 50 kips. And how far away is it from A? 5 feet. It's going down, so it's going to be it's clockwise, so it's going to be negative, right? We have this one that's going down, so it's going to, and you see how it orbits around A in a clockwise manner, so it's going to be minus 20 kips times how far away is that? That would be 10 feet, no, 15 feet. See, 5 plus 10, 15 feet, that's 15 feet away from A. And we have this RYB, so plus, because it's going up, now it's going to go counterclockwise around A. So plus RYB times how far away is that from A? That would be 5, 10, 15, 15 plus 15, 30 feet, right? Summation moments has to be equal to 0, so 0 is equal to minus 250 kip feet minus, that would be 300 kip feet, and then plus RYB, plus RYB times 30 feet, right? So RYB times 30 feet is equal to 550 kip feet. That's not what I wanted. 550 kip feet. Now what's that divided by 30? I don't know. So RYB is equal to, where's my calculator? Turn on 550 divided by 30. 18.33. 18.33 kips, right? So now we can go over here and we can solve for RYA, right? Remember this thing that we set aside? It's very useful. So RYA plus 18.33 kips is equal to 70 kips, right? RYA is equal to 70 minus 18.33, which is no mental math. 70 minus that one, 51.66, 67. 51.67 kips, right? Does that all make sense?
Yeah.
All right, fun stuff. Now, let's just review what we just did real quick, right? Size 50. Right. So moments. What are moments? So moment is a force times a direction, right? So whenever you're taking a moment, you always have to keep in mind you need a force, and a direction whenever you're defining a moment. So it could be kip feet, kip inches, pound feet, pound inches. You know, so always have a force and a direction, right? So why do I bring this up? Well, we also have line loads that we have to worry about, right? These fancy smancy boys, right? We have line load right here. A linear load, I think it's actually called. Line load, yeah. We have a line load right here. It's gonna be 50 feet. It's gonna be 50 feet. So we have this linear load of, let's just say 1. Now let's do 1.5 KLF. Now what does this mean? Well, this linear load deals 1.5 kips per linear foot that spans, right? So what does this mean? Well, you see how it spans 50 feet, right? So 1.5, we're just going to multiply those together. 1.5 kips per linear foot times 50 feet, right? That would just result in 75 kips. And that makes sense, right? 1.5 kips per linear foot, right? This is another way to see it. Times 50 feet. See how these two variables just cancel out. 1.5 times 50, and you're just left with kips as the remaining value variable. I don't know. Right. So whenever you're taking a moment, right? So let's just see. Let's just resize. Right. So now, what do we do with this information? Well, now we can figure out moments, right? So let's just take this moment at B right here. Now what's the moment at B? Well, let's just take summation of forces real quick. But this is not really the point that I'm trying to get to, but you know what, we'll just do with this. Let's do this. So summation of forces counterclockwise is positive moments. Summation of moments at B. Right, so we have this force right here. We have this reaction and reaction of the pin in the y direction. Reaction at the y at A, and R X A. And then we have RYB. So you see how RYB is pointing directly at B, so we don't count that whenever we're taking summation moments. RXA pointing directly at B. It's not 100 feet away from B. No, you see it's pointing directly at B. RYA, on the other hand, is 100 feet away from B. So RYA times 100 feet, that would be negative because it's going in it does a little clockwise fashion. Right, so this 1.5 KLF, right? So we figured out earlier what the force was, right? But so we're just gonna do that right now, right? So we're just gonna have the 1.5 KLF, multiply it by the 50 feet, right? Because that's how far it spans. But remember, summation of moment. When we're taking summation moments, all your variables have to be moments. And we solved this earlier. All we get is a force. We also have to get a distance. So how far away is this from B? Well, you can just take the average, right? So right in the middle, because it's just a line, right? When you take the average, you can just take the middle, and it's just easy conversion, right? So so you can see the start of it happens 50 feet away. Its span is also 50 feet. So divide that in half, you get 25 feet. 25 feet. Remember, this point is the center of the line load. So we take use the distance that's from here to here, right? So 50 feet plus 25 feet would be 75 feet. And then you can just solve that out. I'll do it because why not? So.
Wait, do you mind repeating that?
Which bit?
How did you get the 25 and 25?
Right, so whenever you're taking a moment, so you have a linear load, correct? So you still have to take in, whenever you're taking moments, you still have to figure out how far it is away from the where you're taking the summation of moments, right? So you can't take the distance from the start of it, right? Because that just doesn't make sense. You can't take the distance from the end of it. That doesn't make sense. You would just take the average from the middle. So you see how it spans 50 feet? If you cut 50 feet in half, you get 25 feet and 25 feet. Does that make sense?
Oh, okay, I see. Yeah.
Beautiful. All right. So now you found the middle. So 25 feet plus 50 feet, that would be 75 feet. And then you just solve that out. RYA A times 100 feet equals 1.5, 75 times 75. That's a big number, 5, 5, 6, 25, kip feet. And then you have RYA is equal to, let's divide that by 100, so RYA, so you see how you're dividing by 100 feet. So kip times feet, you take away the feet, so you're just left with kips, and you're dividing by 100, so it'll be 56.25 kips. And this makes sense because RYA is a reaction vector, a reaction force, so in the units kip, makes sense. That'd be cool. Right? All make sense? Any questions?
So if we wanted to continue further on this one, we would have just done like the summation of forces in the X and Y and then plugged in RYA to that.
Yeah.
Cool.
So you just, RXA would be equal to 0, and RYB, that would just be 75 minus 18.75.
Gotcha. Cool.
So, right, so the linear loads and the point loads, they'll all, like, you might get a freaking diagram that looks like this, right? So you have a load right here, you have a load right here, and you have a linear load right here, and then you just know the points. They give you the points, so you know how to take the moment. So just make sure you keep all this in mind, and just do all that. But if you happen to get a problem that appears on one of these handy dandy shear moment diagrams that Klebus gave us, you'll be fine. You just use these values right here, these equations, and easy shortcuts, because you don't want to do all this handiwork every time you want to figure out a problem. Right. Anything else? Great, fun stuff. Let's move on. So now we know how to take summation moments. What else can we do with that? Well, remember cables? Oh, jeez. Remember cables? Remember these boys? Yeah, those were fun problems. These are way too big. Right, so we have two pins supporting a singular cable, and then we have two loads right here, right? So remember, what is the, well, let's define some distances first as well. This will be 10. Probably type that out. I haven't been typing these. 10 feet right there. 15. No, not that number. 15 and another 10 feet, right? So symmetrical, which is fun. And just to further add on to the symmetry, we're gonna have 50 kips right here, and 50 kips right here. Fun stuff. Right, so remember pins, there are two reactions. There's an X direction and a Y direction. Reaction in the X for A, we're gonna call this A, B, C, D. That looks like a D. RYA, we have RYB, XB, right? I'm also gotta find this distance as well. We're gonna call that, let's keep it simple, 10 feet, right? So what do we do with this information? Well, let's start taking summation, start taking summations, right? Should be fun. Right, so summation of forces in the y direction. Summation of forces. Well, let's do summation of forces in the x direction. So that sounds fun. Right is going to be positive. So we have Rxa, it's going right. Rxb, it's going left. I drew it going left, so we're going to do minus Rxb. So Rxa is equal to Rxb. We don't know what that is yet, so we're going to put that in our backlog. Just going to put that in the corner right there. Summation of moments in the y direction, right? So just clear up some space. Summation of moments in the y direction. Assume that up is positive, summation of forces in the y direction. We have Rxa, Rya is going up, so it's positive. We have this 50 kips right here at C, so it's going down, so it's minus 50 kips. Another 50 kips going down, minus 50 kips. Ryb plus Ryb, it's going up, so it's plus. So Rya plus Ryb is equal to 100 kips, right? Have I lost anyone? Just making sure. Have I lost anyone?
I am found. I'm very found.
Beautiful. All right. So now we're gonna take summation of moments. That's a janky sigma. Summation of moments. Oh gosh. Summation of moments is equal to. We're gonna take summation moments at A. At this point right here. Gonna color code that green. Take summation moments right there. So Rxa pointing directly at it, 0 feet away from it, so we're not going to include it. Same thing for Rya, it's pointing directly at A, so we're not going to include it. It's 50 kips is not pointing directly at A, so the 50 kips. How far away is this from A? Well, it's 10 feet. Now, why not this distance, you know? Well, if we just draw a line right here, you see that that right here is where it's perpendicular. You see how it just rotates around like on this axis? Like it doesn't rotate around this axis, you know? So, but because if it would rotate around this axis, the vector would have to be going this way. We see how it's going directly down, so as we draw a line directly down, see that the circle, this orbit that draws around the point is 10 feet. Right, so it's 10 feet away from A, and then it's going to be negative, right? Same thing for this 50 kips. Minus 50 kips times 25 feet, right? Draw a line. You're going to extend this vector, right? So it becomes a line. The orbit that it makes around A has a radius of 25 feet, right? Cool. And then we have Rxb that is pointing directly at A, so look at this. We're going to extend the line. So that extend the vector into a line. You see how it goes directly through A. 0 feet away from A, so we're not going to include it. And then we have RYB, that's going in the counterclockwise, so finally a positive value, RYB. And how far away is that? 10 plus 10 plus 15, that would be 35 feet. Right? So RYB times 35 feet equals minus 500 kip feet. Minus, that's a 1,250 kip feet? I think so, yeah. 1,250 kip feet. I forgot kip feet right there. This is actually positive because I moved to the other side, positive break. So these become positive, this moved to the other side, these are positive now, plus 500 kip feet, plus 1,250 kip feet, so RYB times 35 feet is equal to 1,750 kip feet. Take our calculator out on 1750 divided by 35. That'll be 50. RYB is equal to 50 kips. Did I lose anyone? Fun stuff. All right, so what can we do with this information? Well, now we can do something with it. We can plug it into RYB right here, or RYA plus RYB equals 100 kips. And you just solve that out. RYA plus 50 kips equals 100 kips. RYA equals 100 kips minus 50 kips, so RYA is equal to 50 kips as well. That's not right. 50 kips, right? We have another 50 kips. Fun stuff. So now, what do we do for right, now we can solve for RXA and RXB. What is one thing we can do for this? I didn't really think this far ahead. Shoot. Oh, right. I think what we can do is we can just cut it in half, and then we can determine shear, right? I think so. Yeah. We're just gonna cut it in half, right here. Right. Yeah. So we're just gonna call this E. We're just gonna smallify all this. Just gonna smallify everything. All right, so we just cut that in half. So now we have this diagram right here. So we have E, we have D, and we have the pin right here. We have the RXB. We have the 50 kips right here that we determined earlier. We have the 50 kips right here that was given to us. RXB. So whenever you cut something open, you have a shear reaction, an axial reaction, and a moment reaction. This is V, this is P, and this is M. So P, E, V, E, M, E. I'm just going to move that better. M, E, right there. We have a axial reaction, P, E, and we have a shear force, which is direct, and we can point it directly at it, V, E. Right, so you can take summation of forces. let's take in the y direction first. Actually, Fy is equal to up is positive. So we're gonna determine the shear force, right? We don't know what that is right now. So we have up, that's VE. We have a down 50 kips, so minus 50 kips. We have an up 50 kips plus 50 kips. And then we have, so this has to equal to 0. And these cancel out, so VC. So there is, or VE. Gosh, that's a VE. VE minus 50 kips plus 50 kips. And so VE is equal to 0. There's 0 kips of shear force. Fun stuff. And then we can take summation of forces in the x directions. Fx right is equal to is positive. We have a PE minus RXB. PE is equal to RXB. But that's not really helpful. That doesn't even look good. PE RXB. That's not helpful at all. Now we'll do summation of moments, right? That's the next step. Summation of moments at E. That's where we cut, and we already have a moment there. So a moment at one place doesn't apply to any other place. It only applies to this location right here, right? Because the moment it has to orbit around here. If it was a moment that was 1 foot away, or for a moment that was 100 feet away, see, it has to circulate around here. So whenever you're taking summation of moments and you are already given a moment, you have to take summation of moments right there, and you have to include it. Right. So remember earlier how when we take summation of moments, we have forces. So you see how this RYA is pointing directly at A. That's 0 because it's 0 feet away from A. But if we're taking moments and there's a moment there, you have to include it. And you have to take your summation moments right there. So we have ME, that's going counterclockwise direction, fun stuff. We have the minus, because this is going to go clockwise. Minus 50 kips. Now I forgot my distances. We look over here, this was 10 feet. This was 10 feet, and we cut this in half, 15 divided by 2, 7.5 feet. Fun stuff. So this 50 kips is 75 feet away from E times 75, 7.5. My bad. 7.5 feet. You have this 50 kips, right? This 50 kips going up. That's going counterclockwise. So plus 50 kips times 17.5 feet, right? We extend this line. You see how the circle that goes around the orbit, its radius of 7.5 plus 10. This entire distance right here, 10 plus 7.5 is 17.5. We have 17.5, and we have this RXB. This dimension was 10 feet. We have this RXB. This is peculiar. Extend this line out. See, it has to go all the way over here until it can start to make an orbit around here. So see this orbit that's made, and you see this distance right here. Now, what is this distance? That's this distance, which we stated earlier was 10 feet. So we have, and which direction is this going? This is going counterclockwise. We have a plus RXB times 10 feet. Right now, we're getting somewhere, I think. Oh, geez. I hope we are. We might not actually. I don't remember how to solve this. All right, but we're just gonna keep going. Geez. So half 0 is equal to ME minus 375 kip feet. Kip feet plus 375 kip feet plus RXB times 10. Yeah, we're not gonna get anywhere with this, Jesus Christ. ME plus RXB times 10 feet equals minus 500 kip feet. I did not prepare for this. Shoot. Frig. Cables. Wait. Shoot. Wait a second. I'm doing something wrong here. Hmm. Shoot. I can't find it. Yeah, I can't figure this out. Shit. Oh, fuck. Yeah, there's something I'm missing. I have to. Alright, we're just not gonna. We're just not gonna. Jesus. We're just not gonna talk about that. Yeah, we're just. I can't. Yeah, let's just forget this problem. Maybe I'll figure it out later, but yeah, no. Let's just move on. I can't remember. Yeah, let's just move on. Right. Fuck. Maybe I'll remember. I probably won't. Anyway. Oh fuck. Okay. Jesus.
It's all good. It'll probably come to you later.
I doubt it. Alright, I think we can just skip over that part. Ooh. Axial compression. Yeah, sure. Actually, let's just move on. Right. Okay. So, all right. Now the fun stuff. Second semester. We have linear elastic springs. Right. Linear elastic springs. So we have a lot of new variables that we have to go over. So let's just start with what I'm feeling right now, stress. So sigma, lowercase sigma, I think that sigma is for stress. And this is measured in the units of KSI, so kips per square inch, a force over an area squared, or a force over an area, right? No, that is an axial force. Remember when we did moment reactions, internal reactions? P was axial, V was shear, and M was moment. So we have axial force. And as we all know, that can be measured in kips or feet. Let's not do that. Kips or not feet, Jesus. Kips or pounds. Yeah, pounds. So it's a force. And then we have obviously area. That's measured in inches squared, feet squared, right? So one of the formulas you should know, stress is equal to force over area. Fun stuff. Now what can we do with this? Well, let's get into elastic modulus real quick. Elastic modulus. We have elastic modulus. Now, what does this mean? This is measured in KSI. Just gonna do little things on the eyes. KSI kips per square inches. So what is elastic modulus? Well, that is just a that's sort of like the strength of a material almost. So jeez. That's this. So it's an innate property of a material that you're given. So like steel is like I think 29,000 ks has elastic modulus of 29,000 ksi. Wood has like 1.5 thousand ksi or something. So it just sort of determines like the strength essentially of a material, right? So now you have what? Yeah. So L is length. Gotta define that real quick. L is length, which is measured in inches or feet. Now why do I bring all this up? Well, now we get into deflection, which is in delta. That's lowercase delta. This is uppercase delta, which is the triangle that you see in like in physics or something. But I'm just going to use lowercase. So lowercase delta, that would be deflection. Now deflection, that's measured in inches or feet. Inches, comma, feet. Right? So now what do we do with this? Well, there's a formula for this. Deflection is equal to axial force times length over area times elastic modulus. I think this is for this is in general actually. Yeah. So this is just a formula you should know. I think this applies to like all things, fairly certain. Gosh, I did not prepare for this. Okay, so right. So you also have inertia. Inertia is represented by I, inertia. And that is measured in inches to the fourth. And we have section modulus. section modulus is measured in inches cubed. Now one main thing that you should know with inertia and section modulus is that these are based on the shape of your thing, of whatever material you have or whatever beam you have. So let's say you have steel beam, you have a typical wide flange beam that's terribly out of proportion, right? So if you had a steel beam that had a cross section of this shape, and you had a wood beam exactly the same with the exact same shape as this right here, they would have the same inertia and they would have the same section modulus. So inertia and section modulus are based on the shapes of what sort of members you're working with. So inertia and section modulus are also related to each other. Section modulus is equal to inertia divided by the overall height, half of the overall height of a member. Yeah, I think that's most of it. Okay, yeah, strain, that's lowercase epsilon. Strain, that is just deformation from stress. So I'll just show you the formula. This doesn't have, it's unitless, so it's almost like a percentage almost. There's no units for it. It's just a number. It's not like it's measured in kips or feet or inches. It's just a number. And so strain is just deflection of a member divided by its overall length, right? Let's say you have, let's say you have a member that's like 50 feet long, and then it deflects 1 foot. This deflection right here, because there's a load right there. It deflects 1 foot, so 1 over 50. That's just its strain of this specific member would equal, that'll just be 0.02, right? That's 1 divided by 50.
Real quick, for the section modulus, it's I over 5 times H?
0.5 times H, half of H.
Half of H, okay, cool.
Now what? Let's see. I think that's all for now. It's all for units overview. Right. Oh yeah. Okay, yeah, I got that one. All right, cool. So, I'm just gonna make this smaller. Now we are going to do something with this. I'm just gonna pull something up. Well, I'll just make it up. So calculating inertia of a wide flange beam. I think we already went over this in class, but I'll just go over this really quickly. So remember, we're gonna calculate inertia, right? So inertia of a rectangle, right? So you can see this those wide flange beams. You can divide into 3 rectangles relatively easily. You have this one right here, this one down here, and this one in the middle. You can also divide it up into like 5 if you want dumb fun. 1, 2, 3, 4, 5. Or you can divide it up into 4, or you can divide it up however you want. It'll all work out, surprisingly. But we're just gonna stay simple. We're gonna divide it into 3 rectangles, right? So the inertia of a rectangle, well, inertia of a group of rectangles is equal to summation of base times the height cubed over 12 times area times d squared, right? Remember how I said inertia is measured in inches to the fourth? To see b, that's how long the rectangle is times h cubed. That's supposed to be a plus. That's supposed to be a plus right there. Geez. BH cubed over 12 plus AD squared. Yeah. So B, that's one measurement of, that's 1 unit of length. And then H, that's 3 units of length, 4 units of length. That would be equal to, that would fit in with inertia, right? And then same thing with area. That's 2 units of length. And then we have D squared, which is also 2 units of length. So that would be 4 units of length. Inches to the fourth. Fun stuff, right? So let's have this wide flange beam. Let's just be a little different. This is gonna make this 6 inches tall. This is gonna be a tiny boy, right? And we're gonna make this 2 inches long. Now this thickness is gonna be, one 1/8 of an inch, and this thickness right here is gonna be 1/4 of an inch. Right? So these are called flanges, and this is called a web. So flange thickness is 1/4 of an inch. The web thickness is 1/8 of an inch. The overall span, the length, I forget, is 2 inches, and then the overall depth of it is 6 inches. I gotta find the right terminology. What's the right terminology? Let's see, right there. It's called, it's just width. Yeah, width. Okay, yeah. So the flange width is 2 feet, right? 2 inches. 2 inches. 2 inches. This is a tiny wide flange beam. 2 inches deep, 6 inches tall. 1/4 of an inch web flange thickness, and 1/8 inch web thickness, right? So we have our 3 rectangles, one right here, one right here, one right here. So we're just gonna plug all that into here. So for one, we're gonna solve it for one of the rectangles. So we're just gonna put that right here. That would be B, that would be 2. We're just gonna solve for that, this down one right here. 2 times H. That's 1/4 of an inch. This is 2 inches cubed over 12 plus A. What's the area? 1/4. That would be just 0.5 inch. 0.5 inches squared. I don't like this. 0.5 inches squared. Okay, that's, yeah, 0.5 inches squared times D. Now what's D? So what's D? So that's the distance. That's the average distance of this shape from the neutral axis of the shape. So what's the neutral axis? It's just like this, the center point of the entire shape. So we're just going to cut right through the middle because it's symmetrical. It's a symmetrical shape, so it's going to cut through right through the middle right here. This is also a symmetrical shape, which is fun stuff. So we're going to cut through the middle right here. So we're going to find the distance between here and here. Now, what is that distance? Well, we know this entire span is 6 inches, right? It's going to redraw it over here because, well, you know what? We know this entire span is 6 inches. So we know this. So we know this span right here, 3 inches. But we have this little thing right here. And remember back in the line loads, we we'd have to take the average of the linear load. Well, it's kind of the same thing here. You just have to take the average of here and then add to this distance. But what is this distance? This distance right here is overall distance right here minus this thickness right here. So distance from the edge of the flange to the neutral axis is 2.75 inches or 2 3/4. And then you just, so you would have to divide this by in half. So each distance right here, there's a distance right here, and there's a distance right here. And each of these is 1/8 of an inch, 1/8 of an inch. So you take this distance right here, so right here plus that one, and then you would get 2.875 inches. And you also square that, because formula. I'll add all that together. Well, let's actually solve this out real quick. 2 times 0.25 times divide by 12, right? So very small, 0.002, we're just going to call that 0, plus, now here's the crazy part, 0.5 times 2.875 times 2.875. Look at the difference. Look at the difference. So you see, this part of the equation didn't really matter that much, but what really mattered was the distance. The distance was a huge player in how far away it was. Like obviously you still have the area, which is a pretty significant player, but also the area also takes, well, components of the area is taken into consideration here. So it's really interesting seeing that a majority of the work comes from distance over here, right? We have 4 inches to the 4th right here for this flange right here. And then I don't want to do all the work, so this one is also 4 inches because symmetry is fun. So we're just going to take this middle one right here. Just going to do, that's not 2 inches. So thickness is 1/8 of an inch times, what's the height? Well, that would be 6 inches minus 1/4 minus 1/4. We're taking this entire distance right here. So that would just be 5.5. Yeah, 5.5. 5.5 inches times cubed times 12 plus what's the area? That's 1/8 times 5.5. Well, I don't know that, so I'm just gonna 5.5. 0.6875 times the distance. Oh wait, what's the distance? Well, it's right here. It's 0 times 0 squared. So this stuff sort of cancels out. So now we're just left with this, which is 1.7. So the inertia of this rectangle is 4, inertia of this rectangle is 4, inertia of this rectangle is 1.7. And remember, this is all based on where the neutral axis is. And you just add all this together, so you get 9.7 inches to the 4th for this thing right here. Any questions? Did I lose anyone?
So in the end, to get the inertia of the entire wide flange, you just add the middle one plus both of the top ones. Okay.
Yeah. So you see summation of all these formulas.
Okay.
Right. Where do I go from here? Right. We can actually also calculate section modulus real quick. Just for funs. Section modulus equals inertia over, inertia over 0.5 h. So overall height is 6 inches. The section modulus would equal 9.7 inches to the fourth over half of the height, which is 3 inches. And that's like around, I don't know, like 3.23 inches to the cubed. Yeah. 3.24 inches cubed. Close enough. Right. So what can we do with this? Well, now we can calculate deflection in a beam, right? Oh gosh. So now let's just minimize. Jesus. Minimize all this jargon. Okay. Now what can we do with this? Well, we can. Where is it?
So deflection is PL over AE, right?
PL over AE, yeah.
Okay.
Right, so let's introduce a new variable real quick. Yield strength. Yield strength. So yield strength is very useful because this is yield strength. So this is actually in terms of KSI. Now what else is in terms of KSI? Well, elastic modulus, but this is actually a direct representation. Well, a representation of stress. Yeah, stress. So whenever you have something, like let's say a beam, you have a certain stress that's applied to it, right? But let's say you want to determine a limit for that stress. Well, you would define the limit in terms of yield strength. So stress would be the actual stress that comes out of a problem, but the yield strength is sort of the upper limit of what you want your stress to be. So it's sort of a threshold. So right. So one thing that I have. Jeez. Oh, okay. So another interesting formula. Sigma is equal to moment over section modulus. So that's just another formula to keep in mind.
For the stress, yeah?
For stress, yeah. And then you have the stress. You also have the stress, which is equal to 0.66 of the yield strength, right? So you know there's like an upper limit of the yield strength, right? Let's say the upper limit is freaking 100 KSI, right? obviously you don't want to go over that, right? Because let's say you have building and you calculate for the building to have like a floor to have a force of 100 KSI, right? Well, sooner or later, like there's gonna be some dummies who like show up there with and somehow generate a force of 101 KSI, you know? So you have to sort of account for this sort of these fluctuations of stress that something's going to handle. So that's why you have to multiply by 0.66, approximately 2/3, to get your actual stress. So stress would equal 0.66 times 100 KSI. So your stress would equal 66 KSI. So now when you have it built, so now you make your building, let's just say you make your floor to support 66 KSI, right? That's like the maximum, like from all the calculations that you've considered, dead load, live load, others, like whatever loads you can consider, you calculate 66 KSI, right? And obviously, because of how live load works, it's not going to be accurate. It's going to fluctuate. It's going to go up. It's going to go down. But you know, when it goes up, you know, it'll go up to like 70 KSI or 80 KSI. You know, like it'll be fluctuating, but you know, it'll also go down to like 50 KSI, which is optimal. So it's not putting as much stress on your floors. But you see, it's not reaching this limit of 100 KSI. So it never gets to that yield strength, right? So this is sort of like a safety factor that you take into consideration whenever you're solving problems, right? So just keep that formula in mind. Right, so let's move on. I think I have one more thing. Yeah, one more thing. All right. So this is directly from class, but this sort of just drives home these concepts. So you have a steel beam, right? You have a steel beam of length 30 feet. You can draw these. I'm gonna draw these. Steel beam of length 30 feet. W, what the frick is W? Your weight, I think? I guess that's just linear. Oh, that's like the weight of the beam, I think. 1.5 KLF. Right, and then your yield strength is 50 KSI. And then your elastic modulus is 29,000 KSI. Right. Yeah.
So that's 1.5, right? KLF.
1.5 KLF. Yeah.
Gotcha. Cool.
Now, yeah. Okay. So, what the frick does this stuff? What the frick can we do with this? Well, we're trying to find deflection and inertia, right? So how we go about that? Well, let's take this. Well, let's take your freaking shear moment diagrams. Let's assume this is a simply supported beam with a uniform line load, right? So we have this boy and this boy right here. So this is sort of a visual representation of what the frick this is. So this is 30 feet long, right? You have 1.5 KLF acting upon it. Now, what can we do with this? Well, we can determine the maximum moment right here using this handy dandy formula that appears with the thing, right? So what is this? WL squared over 8. This would be moment, right? The moment is equal to WL squared. Moment is equal to W 1.5 KLF times 30 feet squared over 8, and then you solve that out. So 5 times 30 times 30. So you get 168.75. 168.75 kip feet. So why is this important? Well, now we can take this moment and solve for section modulus. Remember this formula right here? This formula right here? Well, we can actually plug this formula into this formula. So it would, substitute sigma for m over sx. So m over section modulus is equal to 0.66 fy, right? So now we can move this to the other side, so it'll be sx equals sx, it'd be moment over 0.66 fy. Now section modulus is equal to this number. I'm writing that out. This number right here. 1.68.75 over 0.66, and our yield strength was 50 KSI. So our section modulus is equal to this number divided by 50. We should get, that doesn't seem right. Wait. All right, so that's what the fuck? Oh. That's weird. So we should get, oh, right, okay. So there's a problem right here, right? So this is currently in kip feet, correct? I'm just gonna write it out. Jesus. 168 kip feet over 0.66 times 50 KSI. Now, what's the problem with this? We have kips per square inch on the bottom, but we have kip feet on top. So whenever we put this thing together, we're going to have a foot unit, and we're also going to have 2 inch units. So how we remedy that? Well, we're just going to multiply this by 12 inches over foot. So we're just going to multiply that by 12. We're going to change that from 168 kip feet to kip inches times 12. So, and it's just 168.75, but I'm lazy. So we're just going to plug into that calculator. 168.75 times 12. So now this top the numerator is now kip inches. So now we have divide by 0.66, divide by 50 KSI, kips per square inch. So now we're happy. Huh?
Why is it divided? Isn't it 0.66 times? Is it times?
Well, yeah, it's just, I didn't put it in parentheses. It would come out the same because I didn't put it in parentheses. See here, how I put these in parentheses. But if I don't put them in parentheses, I would have to divide it in order to get the same value.
Okay. Whoops. I got you.
So it'd just be section modulus is equal to 61.36 inches cubed. Right, so now what can we do with this? Well, wait. Nothing, because now we found it. I think we can. No, we can't. Right. So now what do we do with this? We're just gonna make this a bit smaller. By that. By that. Right, so we're just gonna, now we're gonna move on to the last bit of the problem. So deflection. So we're given a we're given a deflection as well for this problem that we went over in class, I think, of 1.5 inches. This is gonna be the maximum deflection that we would want in a okay, this makes sense. This is the maximum deflection we want in our beam, and so how do we get to that? Actually, we weren't given that. So there's a few formulas that we were given in class. So one of them was total deflection should equal the length divided by 240, right? So let's say you have a 20-foot, let's say you have a 20-foot beam, that's 240 inches, right? The maximum deflection that it can be is 1 inch, right? You have deflection, so let's say you have a 20-foot beam divided by 240, maximum deflection would be 1/12 of an inch, or of a foot, which would be 1 inch, right? So this sort of formula is also sort of like safety factor, because you don't want the floor to freaking deflect like at an ungodly number, right? So you sort of have limitations with that. So we use this formula to determine the maximum deflection of this beam, which is 30 feet long. That would just be 360 inches divided by 240. So maximum deflection is 1.5 inches. All right, so now this, we can start figuring out.
Wait.
So
it's 240, and that's out of 12 feet, or because the 240 is inches, right?
Well, no, it doesn't have a value. So it's sort of like a percentage, right? So you have a length of a beam, right? So based on how long that length is, you have a maximum how far I can deflect. Like you have this comb, which is a certain distance across, and using this formula, you can determine exactly how much your deflection allows it to go. Right.
Okay, because I saw a 360 against a 240, and then you said it was 1.5 inches. I thought that would be 1 foot, 1 foot, 1 inch, something like that.
No, so it would be 360 inches divided by a unitless 240, so it doesn't change the units, right?
Ah, okay, now I get it.
Right. So now, final bit of structural right here. So remember this freaking thing you got, right? Now there's another formula right here, at the bottom, which calculates maximum deflection. 5 times WL. Yeah, I'll just, so maximum deflection is equal to 5 times W L to the 4th. That looks like not L to the 4th over 384 times elastic modulus times inertia. Yeah, it's called elastic modulus. Elastic modulus times inertia. So now we have this one, we can plug it into there. We're trying to find inertia, so inertia would equal 5 times W, which is 1.5 kLF, L, which is 30 feet to the 4th. Remember, multiply it out to inches. Remember to multiply out to inches over 384 times E, 29,000 KSI times I, or times deflection, because we sort of just, since this is in the numerator position, this is in the denominator position, we can just swap them out. So, and hopefully I did all my calculations correct. 5 times W, 1.5 KLF, that's in per linear feet, so we're going to have to multiply that by 12 to make that, turn that into, divide that by 12. Divide that by 12 to turn that into kips per linear inch, I believe, times L, which is 30. We have to multiply that into inches, times 12, and that would be 2 to the 4th. By open parentheses, 384 times 29,000 times 1.5. Hopefully I did this correctly. I did. So your inertia is equal to 628.44. Right. So inertia. So this is, remember that you calculate inertia from the shape of your beam, shape of the cross section of your beam. So you have to find a beam in order to comply with all these values. You have to find a beam that has an inertia of this or higher, right? So let's say you have inertia with 630 inches to the 4th, right? That would work because it's super strong. But then you get a beam that's 1,000, has an inertia of 1,000 inches to the 4th. That would also work because it's stronger, but you can't have a beam with an inertia of 600 inches to the 4th because that would be super weak and not comply with all these calculations. So inertia has to be greater than or equal to this thing. Any questions? Structural before we move on to environmental.
If we get the chance, if not today, but before Friday, do you think we could do the cable problem again?
Yeah, okay. I'll figure that out over.
Yeah, it doesn't have to be today. Maybe tomorrow or Thursday.
Yeah, because I'm getting very tired. I see a few of you guys are getting tired too. Jesus.
Yeah, so we can come back to it another day. But I do want to come back to it to make sure I understand it at least correctly.
Yeah, totally.
Yeah.
I'm just tired from working all day, my guy. I was laying down on the table for a minute.
Saw that. All right. So let's move on to structural. Brick. Environmental. I am not
all
feeling.
good, brother. It's all good.
Ah, jeez. All right. So let's look at our psychrometric. First thing, we're just gonna go over a few things. Like, jeez, this is gonna take another hour. All right. Let's find the thing. Where's the? Yeah. All right. So we're gonna share this screen instead. Don't save. Share this one. Whoa, would you look at this? Wow. So, psychrometrics. It's called one thing real quick, before we start. Just take a look at this. Psychrometric. There's an R in there. It's not psychometric. Not psycho. We're not going psycho. We're going psychrometric.
I know, my guy. These classes be making me go psycho.
Yeah, so yeah. It should be making you go psychro. So just something that I noticed. I don't know if anyone cares, but yeah. Psychro. Right. So psychrometric chart. So there are essentially two main properties of a climate. There is temperature and there is humidity, right? Whenever you get a forecast, you get a temperature, which is one of the most important things, but you also sometimes get humidity. So right on the bottom axis right here, you have your temperature, dry bulb temperatures. That's just your normal temperature that you would get on a weather forecast. So you see, it goes from 32 degrees to 120 degrees, and I assume this is in Fahrenheit. Yes, Fahrenheit. So 32 degrees Fahrenheit down here. You have 120 degrees Fahrenheit over here. Right. So now you have humidity. So whenever you get a weather forecast, you're given temperature, of course, and that's going to be your dry bulb temperature. You're also given a humidity, and that's normally given in a percentage. So you see these sort of curves right here. Go like whoop right there, swoop right there. That's going to be your relative humidity, right? You see right here, this line represents 90% relative humidity. 80, 70, 60, blam, blam, blam. So let's just plot something. Let's have temperature of 85 at 30% humidity. Fun stuff. Find the 85 right here. Find the 30% humidity. We follow the line over here. Follow this line up. And that's where our climate is. Right? So now what can we do with this? What we can do is now we can start finding wet bulb temperature, right? So if we sort of remember the little sock thing, we fully saturate, we get a thermometer, we saturate it in water, and then let the water evaporate with by adding a little bit of energy to it. You sort of get this wet bulb temperature, right? Which which is like is measured with these lines right here, right? So you have this line right here, and these lines are normally just all parallel to each other. So you can just get one line that's like relatively close to there. So you see there, to see this web temperature right here, you see all these parallel lines, get one relatively close, move it over, and then you find the intersection right there. And then mark that off right there. And then you can follow it down, you see that your wet bulb, or you can use these sort of temperatures right here. So your wet bulb temperature is about like 64 degrees. Right, let's write these over here. Your dry bulb is 85 degrees Fahrenheit. Your relative humidity is 30%. You have your wet bulb temperature, which is a 64 degrees Fahrenheit.
And that's the slant line, right?
That's the slant line.
Okay.
And you can also find what's it called? Dew point, right? So dew point is the temperature at which, at your current humidity, will water condensate, right? So that would be the horizontal lines. Remember, I said it at your current humidity is when water would condensate. So we're putting it on the x-axis because you see this measures humidity, this measures absolute humidity. So we move that down and we see that our dry bulb temperature is about 50 degrees Fahrenheit. So at this current humidity, which is 0.0, so our absolute humidity.
Wait. The dew point is 50, right?
Dew point is 50, yeah. 50 degrees Fahrenheit.
You wrote a B, just to make sure. Just write a P, but you're good.
Oh, fuck.
You're good.
Our dew bulb is 50. No, our dew point is at 50 degrees Fahrenheit. So our absolute humidity is 0.007 or so, and that is measured in pounds of moisture per dry air, pounds of moisture per pound of dry air. Pound of moisture per pound of dry air. I don't know, it's weird. I'm just gonna put 0.0077, right? So at this current climate, it has this absolute humidity. And for any climate that has this absolute humidity, it shares the same dew point. So let's say if you have 105 degrees Fahrenheit at, let's just say 18%, 18% relative humidity, it would have the exact same absolute humidity, meaning it would also have the same dew point. See this entire line, these two are directly related to each other. And then you have enthalpy, which is BTUs per pound of dry air, which I think I sort of consider to have which is the energy or so of a certain thing, of a certain climate, sort of like how much energy it holds. So it takes relatively the same line that wet bulb temperature takes, just slightly off. So it just goes over here. That's like around 29. So your enthalpy is 29 BTU per pound of air, per pound of dry air.
Wait, why isn't it BTU per H?
Per pound of dry air. Dry air.
Oh, it's on the psychometric chart. Okay, that's, yeah, makes sense.
BTU per H is a different thing. That's a measurement of uh, shoot.
Yeah, because that was
Of
something.
heat flow. Of heat flow.
Heat flow. Okay.
BTU per H. BTUs per hour is a measurement of heat flow. Right. So, any questions? Other questions?
Nah, this one I know. There's the U values, the ones I don't really know.
Yeah, we're gonna get into that. All right, moving on. So, y'all remember heating degree days and cooling degree days? Those were fun times. We had an entire worksheet on that. So, what are these? So, these are measurements of just like these are ways to sort of categorize a climate to like pertain to climate zones. So it's sort of like gives you an idea of what a certain climate is like. Is it hot? Is it cold? Is it normally hot or is it normally cold? And how hot or cold is it? So, let's say you have right. So calculating heating degree days and cooling degree days, you have to get the average high or the high and the low of a certain day. So heating degree days and cooling degree days, they calculate. Well, so every day of a year is calculated as a heating degree day or a cooling degree day, and then you would add all this together into a year. And that would help you determine the climate of an area. So heating degree day. Let's just get a high temperature real quick. Let's just get a high of 97 degrees Fahrenheit. So we're in Houston, and we have a low temperature of 69 degrees Fahrenheit. Right, so we have the high and the low. Now we have to calculate the average. So this is for a day. This is like July 1st or something. I don't know. I think it's super inaccurate. This is in December 25th. So December 25th, we have 97 degrees Fahrenheit as our high and low, 69. So to calculate the average, we add those two together and then divide by 2, right? So 97. No, wait, 97 plus. So our average temperature is I just calculated 83. 83 degrees Fahrenheit. So what do we do with this? Well, we have to sort of determine a standard, right? So the standard temperature, normal temperature, is 65 degrees. That's just something you have to remember. Now, is 83 degrees higher or lower than 65? It's going to be higher, so we're going to have to cool this environment down, right? Because it's so hot. So 83 But how much do we have to cool it by? A3 minus 65 degrees Fahrenheit. That would just be, I don't feel like doing quick maths. A3 minus, that'd be 18. 18 degrees Fahrenheit, right? So this would turn into 18 cooling degree days. Now, this is for 1 day, right? Well, let's sort of break apart this sort of word right here. Cooling.
Wait, where did the 65 come from?
65, that's just something you have to remember. This is the standard temperature.
The standard temperature, okay.
Yeah. So this is 65 degrees is what you base your cooling degree days on and your heating degree days on.
What if the average temperature is below 65?
So we'll get into that in a bit.
Yeah.
Cooling degree days. Let's just look at this word real quick, or term real quick. Degree days. Let's draw a thermometer real quick. So you have this 65, which is the sort of standard temperature that you're sort of comparing your temperatures to, right? We have this, but the average is 85 degrees right up here. 85 degrees Fahrenheit. And now this is obviously this is going to be a range between 97. That's 97 and 69 degrees Fahrenheit, right? So you see that and like the average of the day is over 65, so you have to cool it, right? You have to cool it down to the 65 degrees. So cooling degree days, you have to cool it by 18 degrees, right? You have to cool it by 18 degrees. And this takes place, well, this sort of happens for 1 day, right? So cooling, because you're going down degrees, that's how many you're going by. Days, it's taking place in 1 day. 18 cooling degree days. So for 1 day, you would be cooling by 18 degrees. Same thing for heating degree days. So let's say it is, so let's say we have another one, right? We have a high of, let's just go 54 degrees Fahrenheit. .54 degrees Fahrenheit, and you have a low of 32 degrees Fahrenheit, right? So see, this is very low. And calculate the average. And so 54 plus. So your average would turn out to 43 degrees Fahrenheit, correct? So you see how 43 degrees Fahrenheit is lower than the 65 standard temperature. Well, just this baseline that we're using. And so because it's lower, then it's cooler, right? It's cooler than the temperature that we're trying to go for. So we would have to heat up the sort of climate to reach 65 degrees Fahrenheit. So how much do we have to heat by? Well, let's just take the difference between 65 degrees Fahrenheit minus 43 degrees Fahrenheit. And then we get 22. Yeah, 22 degrees Fahrenheit. So that would mean 22 heating degree days. Back to the thermometer. Our temperature that we got was really cold. It was a average of 43 degrees Fahrenheit, right? and the range of it was 54 degrees to 32 degrees, right? So we have to heat it up by 22 degrees to reach 65 degrees. 22 heating degree days. So if your average temperature is lower than 65 degrees, then it would have to be converted into heating degree days. If it's higher, it would have to be converted into cooling degree days. Yeah? Any other questions?
Yeah, so now I'm remembering it can only be one or the other. Either you have to eat
Right.
it, it can't. There's no way it can be both.
Yeah.
Okay.
So let's say you have December 25th has. So you have this day, which it has 18 cooling degree days, would have 0 heating degree days. And for this particular day, you would have 22 heating degree days and 0 cooling degree days. Yep. All right. Any other questions? Cool. Now comes the terrible part, U values. I really did not want to do this, but we sort of have to. All right. Let me just pull up this. Did I print it out? I don't think I did. No. Yeah, no. All right. All right. So we have a wall. Man, we have a wall. Now what's a basic composition of a wall, right? I don't remember. You have a brick layer, and then a I'm blanking. You have a brick layer. What goes right after brick layer? I don't know. Let's just do a plywood, and you have your studs and insulation. You have another thing of plywood and gypsum. I feel like something's off about this.
Don't forget the 2 air films.
Yeah. I feel like I'm forgetting something though. Hold up. Because I feel like okay. Okay. Right. Okay. I'm just overthinking it. So we have just have bricks. We have a brick veneer. We have a brick veneer. We have a thing of plywood. We have our bats insulation. Bat right here, including our studs. And then we also have our gypsum board. Right, so fun stuff, right? So now we have to go into our handy dandy R value thing, right? Am I sharing this? I don't know. Like yeah, okay. So we have our R values in our handy dandy little book that Van Lanningham gave us. So we just have to sort of look these up, right? So we have, so in all wall assemblies, we do have a outside air film. Always gotta remember the air films. I'm getting really tired, so I'll just type it out. Outside air film. Right. So now we have our bricks, brick veneer. We have our plywood, and you'll have like measurements for how thick these are, but I don't know them. For bat insulation, we have our wood studs, which go between our bat insulation, or more like our bat goes in between the wood studs. And we have our gypsum board, and we have the inside air film. So first we have to look up the R values, right? So with our handy dandy little book that he gave us, you just look up the R values. To look them up, and just remember to use. We're using IP values because we're doing imperial measurements. SI values we'll be using metric measurements. So like we'd be measuring in millimeters, and we're in the US, so we don't want to do that. But we have our bricks. And let's just, well, actually we have to do our outside air film first. So what is our outside air? What do you use for your outside air film? You would look in your book, and it would be under moving air because outside there is wind, right? There's wind moving outside. So your outside air film would have a. I'm just gonna be super conservative. So let's just do. Oh geez, I forget.
Right. So by being conservative, he's telling us to pick the lower number, right?
Yeah, pick the lower number. So so like you sort of overestimate, right? Right. So our air film would be, our value would be 0.17. And you have your bricks. That'll just be 0.10. Per inch thickness. Let's just say this is 4 inches. So that would just be 0.4. Just 0.4. Plywood. Plywood would be, it's just like this is going to be 3/8 of an inch. So your plywood would be come out to 0.59. Your bat insulation IP, where's IP? Oh, there it is. Your bat insulation, let's just say, is 3.5 inches. Your bat insulation is 13. With studs. Stud. Where's it? I think it's this. Yeah. I'll just use a number. I'll just say it's 1. Yeah, 1. And your gypsum, let's just say it's this one. Let's just say it's ½ an inch, right? Gypsum of 1/2 of an inch. Just make that. .45. And then your inside air film should always be, I think, wait. No, it shouldn't always be. Your inside air film for this thing should be 0.68. 0.68. So these are all R values, right? R value is a measurement of resistance to heat flow, right? And that's where it makes sense. You see how bad insulation? It's insulation, so it should be pretty good insulation. Its R value is 13. So it's super high. So it blocks a lot of heat, has a lot of resistance to heat flow. Right, so let's just start calculating. So to get the U value is sort of the number which decides how do I say this? U value is sort of how much heat gets through. It's the inverse of R value. So let's say that insulation has an R value of 13, but the U value of insulation would be 1 over 13. These are just inverses of each other, so just be like 0.0769. So it lets less heat through than like if we take the wood studs, we take the U value of that would just be 1. See, it allows less heat to go through, and we'll sort of see that once we calculate U value. This wood stud is driving me crazy. Here, let me actually try to look it up real quick.
And then when you add them, right, it's like this U value is 1 over the sum of.
Yeah.
Okay.
Uh,
Are you trying to find the R value for the wood stud?
yeah. 3.56, I think. Wait. Yeah.
Yeah, I remember when he gave us the homework, he called it a metal stud and played us all.
I'm just looking on the midterm. So the wood stud, that R value he used for the wood stud is 3.56. All right. Cool. So let's just start taking U value. So let's take the U value at the studs, right? So when you think of a wall, so this is a vertical section right here. Let's take a horizontal section, right? So we have the 4-inch bricks, have the plywood. Now we have these studs right here, right? We have these studs. We have these studs, and then we have the insulation right here, right? Just gonna do see if I can do it. That came out better than I thought. Oh my gosh. You have your insulation right here in between the studs, right? And then you have obviously your your gypsum board right there. So this is sort of like a plan, a horizontal section, sort of like a plan view. So you're looking at it from up above. You see the studs right here, and then you see the insulation in between. So if you take a section through here, you see that will cut through the stud and not the insulation. But if you do take a section here, you'll be cutting through the insulation and not the studs. So you have to take two measurements of U values, one that cuts through the insulation and one that doesn't cut through the insulation. So let's just take the U value of a stud at the stud. So it would just be 0.17. This. So at and then between. Right, so we're gonna have the outside air film at, have all this air film, veneer, plywood, gypsum, and inside air for both at and between. So at the stud, we're just gonna say at stud and between stud. At the stud, we're gonna have the wood studs, so we're gonna use that. And between the studs, we're gonna have only the bad insulation. So at the studs, we're not gonna be including the bad insulation, and between the studs, we're not gonna be including the wood studs because it's between the studs. All right, so let's just add all that together. 0.17 plus 0.4 plus 0.59 plus 6 plus 0.45 plus. So our R value for at the stud is equal to 5.85. So we convert that into U. U value is summation 1 over summation of the R values. So we convert that into U value by dividing it by 1 by it. So our U is 0.171. This looks terrible, but we move on. 0.17 plus 0.4 plus 0.5. So our R value for between the studs is 15.29. So our U value, you would just take the inverse of that, the reciprocal. I forget which one is which one's the right one. So you have 0.065. This doesn't seem right, but it's fine, I think, hopefully. Yeah, so one thing you can take sort of observe, so you see how bad insulation has an R value of 13. The wood studs has an R value of 3.56. Now the difference between these is like around 10, 9.5, you know? So you can see that if you've done your math correctly, the difference between your R value should be around 9.5. So if you take 15.29 minus 5.85, it should get 9.44, you know? 13 minus 3.56, 9.44. So it's just another way to double check yourself. So now you have these two U values between the studs and U value at the stud. So now you have to take the weighted average of these. So a majority of the wall assembly is taken up by the insulation, but only a small percentage is taken up by the studs. So take percentage. So let's say these studs are spaced 18 inches on center, and they're 1.5. They're 1.5 inches wide, right? So your U value weighted average would equal, so the ratio 1.5 over 18, right? Inches over inches, that becomes just a ratio. 1.5 over 18 times your R value, this is going to be for the studs, so the U value at the studs would be 0.171, and then you have your U value between the studs, which is just 16.5 inches over 18 inches times 0.065. Put that in your calculator, and then 1.5 divided by 18 times this one.
So the 16.5 comes from 18 minus 1.5. Yeah.
Yeah, 16.5. Yeah.
Gotcha. Cool.
And you have this one, so you should get 0.074. Right, and you see how it's closer to the U value of between, because that's more or less like the majority. So obviously the U value would match the insulation closer. Any questions? All right. I had another thing I wanted to go over, but I'm getting a little tired, so I think I'm just gonna call it here.
Hey man, we can do little stuff and finish this up on Thursday or Friday.
Yeah.
Right. We can continue later and come back to certain things.
Yeah.
So I think today was an awesome review.
I'm sorry, Edison. I was working. I kind of missed structural a little bit, but I was able to overhear a good portion of it.
It's okay. That's why it's recorded. Now you can go back.
Yeah.
Heck yeah, brother.
Yeah.
Hey, Edison.
What's up?
You still got 5 minutes.
5 minutes?
Yeah, you've been recording for 2 hours and 39 minutes. And I said 2 hours and 45 minutes for the whole.
Santos. Dang.
Wow.
All right. Well, I'm gonna stop the recording early, so we don't reach your estimate.
Yeah, see, but hey, that's a pretty good educated guess right there.
That's pretty good.